Hey everyone, welcome back to another video by Camroom 5. In today's video, we are going to be talking about states of matter, particularly the gases. When we talk about them, we need to see what are ideal gases. So ideal gases are the ones which follow certain gas laws under all conditions. They are not vulnerable to conditions. You can't expect temperature changes or pressure changes to change their behavior. What happens is they will follow the gas laws under all conditions. So, what is an ideal gas and what are the attributes of such an ideal gas? Number one would be that they have no intermolecular forces between them. So, they have no intermolecular forces between them. Intermolecular forces, also known as the van der Waals forces, like hydrogen bond, PD-PD attractions, ID-ID, they do not have them. So no molecule attracts another molecule. So what happens is, so when a particle, so when a particle moves towards the walls of the container, when a particle wants to exert pressure towards the walls of the container by colliding with it, there's no particle pulling it backwards. There's no particle which attracts it backwards, and there's no particle decreasing the force of the first particle. That is why these ideal gases exert very high pressure. For example, this is the wall of the container, for example, wall of the container. And let's suppose we have two scenarios over here. The yellow particle, the yellow circle I'm drawing over here is a particle of a gas. This particle is moving forward and it's going to hit the wall of the container, and there is no pull from the backward, there's no pull from behind. So this is an ideal gas, it exerts very high force. But if it was a real gas, if it was a non-ideal gas, there would be another particle pulling it backwards, attracting it towards itself. So the force of the first particle would be decreased because there is also attraction from behind. So the net force forward would be low. So ideal gases exert higher pressure, but comparatively real gases, as we see around us, they exert lower pressure. So this is the first scenario of an ideal gas. The second condition is that particles have no volume of itself, or you can say the particle have the volume of their own. Only the volume or only the space between the particles is considered. So particles have negligible volume of their own, and that is why the volume between them is the only thing you consider. Imagine two boxes over here. In the first box, the particles have literally no volume, or you can say negligible volume of their own. And the space or the volume between the particles is the entire volume. But if you were to talk about a real gases have their own volume. So particles are not point masses, they have their own volume. And that is why you cannot neglect, or you cannot consider the particle's own volume as negligible in a real gas scenario. So in the upper box, there's an ideal gas with no volume of its own, and in the lower box, the particles with own volume are there, so their volume is not negligible compared to the volume between them. And that is why you cannot disregard the volume of the particle itself. So this is the second condition of an ideal gas. The third is that particles will collide totally elastically. So particles collide in a perfectly elastic manner. If you remember elastic collision from physics, elastic collision means that when two particles collide, their momentum and their kinetic energies are conserved. So when they collide like this, which is something that's happening all the time, their momentum, or I should have said their momenta, is conserved and there's no kinetic energy or heat lost. So the velocity of the particles is still the same. But when two particles of the real gas collide, there is some loss of kinetic energy. Perhaps you can say as heat, and you can also say some energy is lost as kinetic or potential energy. So that is why real gases or non-ideal gases do not collide elastically, but the ideal gases do. Now we'll talk about the ABC gas laws. These are the three gas laws that we should know when we are considering ideal gases. The first law is the Avogadro's law, then we have the Boyle's law, and then we have the Charles law. All these laws relate two properties of a gas while keeping the third or the fourth constant. For example, Avogadro's law says that the number of moles of a gas is related to the volume. So more moles of a gas cause bigger volume to be occupied, obviously. Make sure the temperature and the pressure are constant while you are relating the moles of the gas with the volume they occupy. When you talk about the second law, it's the Boyle's law. It relates volume and pressure, and it says that at high pressure gases are compressed, so the volume of a gas, volume of an ideal gas decreases. And obviously vice versa, which means if you decrease the pressure, the volume of the gas expands. Make sure the temperature is constant throughout the pressure and you're also keeping the number of moles of gas constant. The third relationship is the Charles law, which says that a volume of a gas is directly proportional to the temperature taken in kelvins. So at higher temperature, the volume also increases. Make sure you are keeping the temperature in Kelvin and not Celsius. Make sure the pressure is constant throughout this study because there's a relationship between volume and temperature. Graphically saying, if you put moles on the x-axis and volume of the y, so there's a constant straight line relationship. If you put the pressure in pascals on the x-axis and volume in meter cube on the y, it is going to be an inverse relationship. And if you consider the temperature in kelvins with the volume on the y-axis, it is also a straight line with the volume of gas at 0 Kelvin to be entirely zero. The 0 Kelvin is known as absolute zero because there is no volume occupied by gas here. Using these three relationships, we can derive an ideal gas equation, where the volume is directly proportional to the temperature, volume is directly proportional to the moles of the gas, and volume is inversely proportional to the pressure of the gas in pascals. As you connect these three equations, it becomes volume proportional to NT over P. If you put it PV is proportional to the NT, and when you remove the proportionality, the constant you get is capital R, which is known as the general gas constant. So capital R is known as the general gas constant, or you can call it the ideal gas constant. It has a very specific value measured at standard temperature and pressure conditions. Don't forget to notice that the value of R is calculated using the SI unit. So capital R is equals to PV over NT. If the pressure is considered in the units of Newton per meter square, which means basically pascals, and volume is obviously meter cube because that's the SI unit, small n is the number of mole and capital T is the Kelvin temperature. You cancel out everything that can be and your units turn out to be Newton meter per mole per Kelvin. If you realize what's Newton meter, it means force applied into the displacement. So basically that is the work done or energy. So Newton meter is taken as joules per mole per Kelvin. This means that capital R represents the amount of energy supplied to a mole of gas per unit Kelvin change in temperature. You don't have to derive this equation mostly, but you should be aware of the units of R and you should be aware of how we came across this calculation.